Plumb Bob in a car. First, we have to talk about what a plumb bob is. It is a weight, normally pointed at the bottom, so it looks something like this, that is attached to a string that is then affixed to a horizontal support. Okay, and here's the string. What would be the purpose of such an object? A free body diagram is a great way to figure that out. What are the forces acting on the plumb bob? The only forces acting on the weight, or the bob, are the gravitational force, mg, and the tension in the string, F sub t. Both forces act in the y direction, and there are no forces in the x direction. So the point of the bob points down in a perfectly vertical direction, which gives a perfect reference line. This is helpful to people who want to build a house that is straight, or any other constructions that need to be aligned with the y-axis. Wallpaper in a room, a skyscraper, etc. And clearly what the plumb bob is doing is following the gravitational field, right? Because that points to the center of the Earth, and that's what your plumb bob is going to point to. Assume the bob is not moving and is ready to be used as a reference line. We'll apply Newton's second law. Sum of the forces in the y direction is equal to the tension minus mg, and that equals 0 if it's not moving. So the tension is equal to mg. For physics purposes, let's now attach this plumb bob to the overhead light in a car, over here, and accelerate the car forward in a safe manner. Will the plumb bob stay pointing in a vertical direction? Think of what happens to an object on the center console of a car, like your coffee cup if it's not properly secured, when the car accelerates forward. The driver observes the plumb bob swinging backwards and making an angle theta with the normal to the ceiling. It stays there as long as he maintains a constant acceleration. An observer standing outside on the road will see the same angle theta, and the problem will be solved from her point of view, and that's the reference frame where the car is accelerating. What does the free body diagram look like now? The gravitational force is still the same, right? Still pointing down. But tension now has x and y components. The bob is no longer pointed vertically down. Here's the tension. You can see it's going right up the string. What is the source of this force in the x direction? When the car was not moving, the bob pointed straight down. Now that the car is accelerating to the left, the bob is moved. So the force is somehow related to the car's acceleration and the original tension force. Since we now have non-perpendicular forces in 2 dimensions, okay, you have this guy down here, and tension is not perpendicular or parallel to mg, we have to do some vector resolution of the tension force. Once we finish this process, we're going to find another use for the plumb bob. When we resolve the forces, the acceleration of the car will then be found, and we can find it without using any other car gauges, just by doing this angle and some math. We measure angle theta. What are the x and y components of the tension? Assume the acceleration is constant, so the bob is stationary in this new position. In the y direction, we have Fty, it's this guy right here, minus mg, and we're going to say that's equal to 0 because it's stationary. And what is Fty in terms of theta? Well, it's Ft cosine theta. So we do a little algebra, and we have the tension times cosine theta equals mg. In the x direction, the only force we have is the tension force in the x direction that equals max. And what is this force here? That's going to be tension sine theta. And so we come up with this equation, tension sine theta equals m acceleration in the x direction. We're going to stack these two equations on top of each other. Okay, here's the two that we have. The first one is over here, and here's a second one there. What can you say about these two equations? And does anything about the trigonometry jump out at you? Both of these equations define the motion of the plumb bob in 2 dimensions at the same point in time, so they must both be true. Hence, they have simultaneous equations, or system of equations, or whatever you call it. And many times when you try and solve them, you add or subtract the equations to get the solution. But in this case, how about dividing? And now you may be able to see why we stacked the sine on top of the cosine. Because what is the sine theta divided by cosine theta? Well, we'll see on the next slide. And what's going to happen is the tension will cancel out and the mass will cancel out of the bob. So whenever you see a sine and a cosine function, try and get it so you're dividing them. Okay, because then you can get rid of sine and cosine, turns into tangent theta. Right? That's the trig trick. And we already talked how this goes out, the mass goes out, and we now have a very nice little elegant solution here. Tan theta is the acceleration in the x direction divided by g, and the acceleration in the x direction is g times tangent theta. As promised earlier, we're going to find the acceleration of the car without any gauges. All we have to do is measure this angle, and of course the driver is not going to do that. The driver will be safely operating the vehicle and a passenger will be doing this, and we can calculate its acceleration. Note how there's no mass in there, so the mass of the bob does not matter. So let's say we observe that theta to be 11 degrees, so it's not going to look like that triangle certainly. If this is the normal, the bob will swing like that. Not very big, right? That's closer to 11 degrees than this angle. So what is the acceleration? Well, we put that into our formula over here, and we find that the acceleration is 1.9 meters per second squared. And that's about as fast as a four-cylinder compact car can accelerate when it is trying as hard as it can. Hopefully you'll never push the car to this acceleration, so if you have a plumb bob attached to the interior overhead light, it should never exceed an angle of 11 degrees if you want to be somewhat safe.